Okay, awesome everyone. So let me start by just reviewing what we covered last lecture, just very briefly. So the main thing we did last lecture was sort of introduce the idea of a qubit as opposed to a classical bit. So like a classical bit, we had states that we called zero, that we use this notation of a ket where we put it inside these particular asymmetric brackets. And we have a state that we call ket1. But those are really just two elements in a full sort of two-dimensional vector, complex vector space, or really Hilbert space, right? So if in sort of column vector notation, we called the state 0 one of our basis elements, and the state 1 the other basis elements, then we can also have states that look like any linear combination of 0 and 1. If you write like this, in column vector notation would just be the vector alpha. Okay. So that was basically postulate 1 of quantum mechanics. The states are contained in a Hilbert space, and really they're not individual sort of points in that Hilbert space, they're rays in the Hilbert space going out from the origin. So states, rays, Hilbert space. Our second postulate was about measurements. And we're going to make this postulate a bit more general later today. But roughly speaking, said that for every measurement outcome, we have a state and orthonormal basis of the Hilbert space. And the probability of getting that measurement outcome, if you start in state psi, is given by just the inner product of the state m with psi modular squared. And then after measurement, we have this mysterious thing that people call collapse of the wave function, which is a horrible term. But nonetheless, the state becomes this state m, right? For whatever measurement outcome you get. It's no longer in the state psi. Measurements in quantum mechanics unavoidably change the state. And the final postulate we're not going to talk so much about today, but we will talk more about on Thursday, was that the dynamics are described by unitary matrices acting on Hilbert space. Unitary matrices are just basically rotations. They're rotations in this complex vector space, i.e. they're I motivated these things as matrices that preserve the normalization of every state. So someone asked me at the end of last lecture why we should sort of expect that to be true. And I didn't think I really gave a good answer at the time. It is fundamentally a postulate. You can change the rules of quantum mechanics so this isn't true. As Nam pointed out to me after the lecture, one common answer people give to that question is if we look at this rule for the measurements, for the probabilities to add up to 1, then the states have to be normalized. So you need to keep the state normalized so that the probabilities add up to 1. I don't really like that answer because you can define the probabilities for unnormalized states. You just have to divide through by the normalization of the state. But it is a standard answer, and it's one way to sort of get some intuition for why you might expect this. The one I actually prefer is that it means a unitary matrix means that a pair of orthogonal states, if at t equals 0, initial states are orthogonal, then the final states will also be orthogonal. So that means if you can initially distinguish two states perfectly by a measurement, then you can still do that at the end of the experiment, at the end of whatever you've done to it. Again, this is not something you'd like that would have to be true, but it is something that is true, and it's yeah. So the fact that the dynamics are unitary is basically saying that the information at the beginning is still there at the end. Information is preserved. Okay, so today we're really gonna not talk at all about postulate 3. We're going to talk a bit more about both postulate 1 and 2. We're going to start by talking really about postulate 1 for the special case of a qubit. And we're going to see like what the actual space of states look like. We're going to find it's this thing called the Bloch sphere. And then we're going to talk a bit more about measurements. Going to talk about the idea of measurement operators, which is sort of the conventional way measurements are introduced in quantum mechanics. And then, and yeah, we're going to talk about expectation values as well. And then finally, we're going to talk about our first application of quantum information, which is quite exciting. It's a pretty simple one, but it's pretty cool, which is something called quantum key distribution, QKD. Okay? And that's really about, using quantum mechanics to end up with secret numbers shared between me and you, and have complete confidence that no one else knows what those secret numbers are. Something you can't do classically, but you can do using quantum mechanics. Okay, so I should also say, if you want to be reading Riefel and Pollock to get sort of, maybe better explanations than you're getting from the lecture or something like that, then after today, we will have covered all of chapter 2. First half of it was last time, the rest was today. And we'll also have covered the first few parts of chapter 4. Though possibly you should wait to read the chapter 4 part until after next lecture, where we'll talk about multiple qubits and how you define the Hilbert space of multiple qubits. Okay. Great, now time to start the actual lecture. So as I say, we're going to start by talking about this thing called the Bloch sphere, which is really just the space of states of one qubit. Okay, so as we talked about last time, the state of one qubit can be written as alpha 0, ket 0 plus beta times ket 1. So that is described by sort of two complex numbers, equal to 4 real numbers. But we also know that the state psi is the same state as lambda times psi for any lambda, right? So that means that we sort of, one of these complex numbers doesn't really count. It's just a redundant part of the description of the state, where that doesn't actually capture any information about the state. So really, it should be possible to describe the state using sort of one complex number, one complex degree of freedom, i.e. 2 real numbers. Okay, is that clear to people why that should be true? If one of the two complex numbers that we started with, can sort of be eliminated by by multiplying by some alpha to reduce the number of degrees of freedom, then we're really only left with one complex number. So it's a very nice way to sort of parameterize these states, which is that we first normalize psi by multiplying by lambda if necessary. So now we have modulus of alpha squared plus modulus beta squared equal to 1. Okay? If you have two numbers whose squares add up to 1, what's sort of a nice way to parameterize those numbers? Anyone want to make a suggestion? How we could do it? Right, if we have two numbers and we know that their squares add up to 1, then we sort of really only have the freedom to pick one of those two numbers. Anyone think of a nice way that you could, like, you know, parameterize the sort of single degree of freedom that defines both numbers? Something from trigonometry, maybe?
Cosines and sines.
Great, awesome, indeed. Someone said in the chat as well. Yeah, exactly. We can define, say, modulus alpha to be cosine, modulus of beta to be sine, and needs to be, we need some parameter that sits inside the cos and the sine. I'm going to take that to be theta divided by 2 in each case. I could have called it theta. I'm going to call it theta over 2 for reasons that will become clear later. Okay? So now we have that our state psi can be written as cos theta over 2 times some phase that I'll call e to the I chi times the state 0 plus sine theta over 2 times some potentially different phase that I will call e to the I chi plus I phi. Why did I call it that? Just because it's going to make the final answer look simple, but I could have called it anything I like. Times the state 1. Okay? Yes. So all I have done here is I've used the fact that the modulus squareds add up to 1 to sort of reduce the number of real numbers I'm using to describe this state by 1. Right? Rather than having sort of modulus of A and modulus of B be separate, I'm calling them both functions of this thing theta. Okay? Anyone know a way I can now make this even simpler?
You factor out a complex factor, and then you can call that lambda, so that's equivalent.
Great. So just by normalizing the state, I haven't really got rid of my freedom to multiply things by lambda, right? Because I can still multiply by some lambda, which is just a pure phase, right? That has modulus 1, and that won't change the normalization. So in particular, I can multiply by lambda equals e to the minus I chi. Okay? And yeah, that will then make the sort of, it will make alpha real. So we get psi is cos theta over 2 times ket 0 plus sine theta over 2 times e to the I phi ket 1. Okay, so phi can think of as being the relative phase between the coefficient in front of 0 and the coefficient in front of 1. Okay, and that's the thing that actually matters. The sort of global phase, which is e to the I chi, we can just get rid of by multiplying by some lambda. But this e to the I phi is physically meaningful. Okay, great. So we've now parameterized it by two numbers. We have phi, which can be anywhere between 0 and 2 pi, right? Because it's a phase. We also have theta. What's the range of theta we need to have? Anyone want to tell me?
Zero to pi.
Exactly. So we need to have theta over 2 go from 0 to pi by 2, right? So that we can have sort of anything from modulus alpha equals 1, modulus beta equals 0 to the opposite way around, right? Modulus alpha equals 0, modulus beta over 1. So that means theta has to be between 0 and pi. This should start to be feeling slightly familiar here, let me make one further comment that should maybe make it more familiar. If theta is equal to 0, then the state psi is independent of phi, right? Just because the sine theta over 2 is 0, so e to the I phi doesn't affect the state. Okay? What about if theta equals pi? Now the state is just e to the I phi times ket 1, but those are all the same state, right? They're just multiplied by a global phase. So again, state is independent of psi. So we just have one state with theta equals 0, one state with theta equals pi. For any theta in between, we have states for sort of all values of phi between 0 and 2 pi. What does this remind people of? Anyone going to answer?
A sphere.
A sphere.
Awesome. I know you guys know the answers to this. You know it. But just the more interaction we have, the more like people just go back and forth, the better. Okay, so I'm going to awkwardly pause until someone finds the awkward pause too annoying and then answers. So just the quicker you answer, the shorter the awkward pause is. Okay, great. Indeed, this is a sphere, hence the term Bloch sphere. It was not that complicated. This is the usual parameterization where, like theta is a latitude, phi is a longitude, right? Just the usual theta phi parameterization of the sphere. Okay. Let's go up to here. Now we test my ability to draw a circle on my iPad. That is truly horrible, but it will do. Okay, let's think about what the sort of points on this sphere correspond to. Let's start with the point ket 0. Whereabouts on the sphere is this? Someone shout out. What's the value of theta for it?
The North Pole.
Yeah, it's the North Pole, right? Theta equals 0, phi is anything, ill-defined, right? So we have the point 0 up here at the North Pole. What about the point ket 1? Just shout out, guys. What's theta for the south? What's theta for ket 1 and what's phi for ket 1?
South pole with pi.
Yep. So theta is pi, phi is anything. It's the South Pole. Okay. What about the state that I briefly called plus yesterday, which is 1 over square root of 2, 0 plus 1. It's a slightly harder one. Anyone want to give me theta and phi?
Phi is 0 and theta is pi over 2.
Indeed. So we have sort of the same amount, same magnitude in front of 0 and 1. So theta, cos theta over 2 and sine theta over 2 need to be the same. So theta has to be pi by 2. And the coefficient in front of 1 is positive and real. So that means phi equals 0. So I'm going to put this one, this is on the equator. I'll say phi equals 0 is over that side. What about the state orthogonal to plus, which you can call minus, which is 1 over square root of 2 times 0 minus 1. Come on, guys. Opposite, indeed, it is on the opposite side to plus, right? So theta is the same as before because the magnitudes are the same. But now we have minus 1, which means e to the I phi. We have to have phi equals pi. So it's the opposite side of the sphere over here. And we could also have 2 more points called plus I and minus I, which is just 0 plus or minus I times 1. Again, they're an orthogonal pair. And these are going to be at the front and the back of the sphere. So that is meant to be the back, and the front is here. Okay. So what we notice is that each of these sort of orthonormal bases are corresponding to an axis of the sphere, right? So orthogonal states, the opposite poles of the sphere. This is something you'll prove in your problem set. And in fact, it's more general than that. It's the sort of inner product between two states is entirely determined by how far apart they are in the sphere, the sort of angle between them in the sphere. It really is just sine of the angle between them divided by 2 squared. So cos of the angle between them divided by 2 squared is the inner product squared. Okay. So that's about all I'm going to say on the Bloch sphere, other than to make some final comments, which is this is sort of a really nice way to visualize the states of the qubit. It's going to be very useful whenever we're talking about one qubit. The moment you talk about anything more complicated, it sort of the intuition of having a sphere just goes completely out the window. So comment is not a sphere for higher than 2-dimensional Hilbert space. By not a sphere, I mean not like a higher dimensional sphere. It's some more complicated thing that it's really hard to visualize. I mean, visualizing higher dimensions is hard enough anyway. But it's actually a space called complex projective space that has some complicated topological structure to it. So yeah, basically, whenever you're thinking about one qubit, this is great. Otherwise, probably not terribly useful. But yeah, the thing to really take away from thinking about the Bloch sphere is that the sort of actual dimension of the space of states is one complex dimension or 2 real dimensions smaller than you might naively think from just looking at the number of numbers we need to specify psi. Okay.
I had a question. So we have to include that relative phase because it's physical. Is there a justification for that other than like when you're looking at the time evolution of superpositions, it comes into play, or is there easier way to see that?
So the way to see it is that it can affect if 2 states have a different relative phase, then the modulus squared of their inner product will have a cross will be different. Yeah, exactly. Yeah. So the reason the global phase is sort of irrelevant is that it cancels out when you look at the inner product with state with itself or the inner product with state with anything else, but you look at the modulus squared, right? And the modulus squared is what determines it, measurement probabilities. So yeah, that's why it's physical. But it's also just postulate 1 was that states are associated with rays. The relative phase changes what ray you're looking at, right? It's not just multiplying by some global lambda, so it changes the state. Okay, that's really all I mean by physical. Okay, awesome. So that is all we're going to talk about the Bloch sphere for today. So I'm now going to switch topics, and I'm going to talk about the measurement postulate. So just to review yet again. As we defined it yesterday, or Thursday, last lecture, measurement postulate says you have orthonormal basis of states that we can call ket m for different m's, okay, where M is each measurement outcome. I want to emphasize here, by the way, M does not necessarily have to be a number, right? So M could be whatever you're happening to measure. Yesterday, when we were measuring the polarization of a qubit, then M was just, vertical or horizontal, for example. There were the two values of M. We could have called them a number. We could have called them 1 and 0, for example, but we didn't have to. It's really just any label we want to have that we associate with each measurement outcome. And then step 2 of the measurement postulate was that conditioned on getting outcome M, the new state of the system is ket M. So there's a sort of problem with this definition, or it's kind of limited in a certain way, which is that it only makes sense if we're sort of measuring every property of the entire system, right? We're like each orthogonal state in the basis corresponds to a different measurement outcome. But in the real world, the universe has a very, very big Hilbert space to it. And when I do a measurement by looking at this screen and seeing that it's working, then I haven't measured every single property of everything going on in the universe, right? So it seems a bit crazy to say that, to define that measurement, I need to talk about like how different outcomes in the measurement depend on like what's going on over near Saturn or something like that, right? Because that just seems completely irrelevant to the state. It seems like there's a lot of different states the universe can be in that I would call the same measurement outcome, because I just don't see anything that distinguishes them. Okay, so what we're going to talk about now is what happens if your measurement doesn't uniquely determine the state. I'll call that a partial measurement. So to give a very simple example, let's consider what's called a Q tripped, tr for 3. So this is just like a Q bit, except instead of having sort of 2 states forming the basis, we call 0, 1, then we're going to have 3 states, which we call 0, 1, or 2. Okay? And I could want to say I want to do a measurement where I measure whether the state is sort of odd or even. Okay, it's a reasonable thing I might want to do. But using sort of our rules for the measurement postulate, it's not really clear how to do it. So let's say I have some state psi that looks like C0 times 0, 1 times 1 plus C2 times 2. What do you think the probability that I get an outcome of this measurement saying that the state is odd is? Anyone? This is one that's kind of obvious what it should probably be.
C1 squared, or absolute.
Yeah, exactly. Great. So modulus of C1 squared seems to be the obvious thing. And then, given that outcome, new state is presumably going to be state 1, right? Because that's the only state that we can that is odd. So, based on what we were saying before, it seems like the obvious thing. Okay, what about the probability that we get an outcome even? Again, should be able to work out what the answer to this is. Anyone?
C0 squared plus C2 squared.
Awesome. So it is indeed C0 squared plus C2 squared. There's a couple of ways you could have worked this out. You could have said, oh, imagine if we measure what the actual number is, whether it's 0 or 1 or 2, and then we add off all the probabilities of getting an even number. That works. The other way you could have said it is that there's only two measurement outcomes, odd and even. We know what the probability of getting odd is, so probability of getting even must be 1 minus that, right? And since our state is normalized, that's modulus of C0 squared plus modulus of C2 squared. Great. But the harder question is, given that we got an outcome, measurement outcome that said the state was even, what is the new state? So our rules before were that the new state should just be ket m. That's just the answer, right? But what is ket m at this point? It could be ket 0, could be ket 2, could be some superposition of the two of them, right? Because that's still like definitely even if I have just a mixture of 0 and 2. Anyone want to guess what the answer actually is?
Alpha times ket 0 plus beta times ket 2.
Yeah, what would alpha and beta be here?
Just C0 and C2.
Yeah, so that's a good answer. That is indeed the right state. So the answer is indeed sort of C0 times ket 0 plus C2 times ket 2. There's only one thing you can maybe change about that, which is, as written now, the state isn't normalized, right? Which is fine. That still means the same thing, but we normally like to write things normalized. So to fix that, we can just divide through by the normalization of this state, 1 over square root C0 squared plus C2 squared. Okay, so this is indeed the right answer. It's sort of, if C0 was 1 and C2 was 0, then you'd like the state to end up being specifically 0 rather than being 2, right? And vice versa. And for a superposition, it just sort of looks like the superposition you had before. But that does not follow from our postulate 2, because our postulate 2 didn't know how to talk about a measurement that doesn't distinguish all three states in the basis, right? So let us now define a sort of more general version of postulate 2. Which is going to be the following. So for each measurement outcome M, we're no longer going to have a state ket M. We're instead going to have what's called a projector operator, which is I'm going to call PM. Okay, so what is a projector? Change color maybe. Projector is defined as an operator such that P squared is equal to P. In other words, eigenvalues are all 0 or 1. Okay? Is that clear to people? If that's not clear, please ask. So an example, yeah, we'll see examples in a minute. Step 2 is going to be that the probability of getting an outcome M is going to look like bra of psi times PM. Sorry, I should have had an extra condition here. we need to have all these projectors. When you add up the operators, you need to get the identity operator. Okay, that's just our rule. You'll see it in practice in a minute and it will make more sense. The probability of getting an outcome M is just going to be bra psi times the operator PM times ket psi. And then finally, the new state, given an outcome M, is going to be PM acting on the state psi. So psi projected into that space PM divided by the normalization factor, just to make this state normalized. Okay, let's see how that would have worked for our operator that measured whether our Q-trit was even or odd. Okay, a projector P odd would just be the outer product of a ket 1 with a bra 1. In other words, as a matrix in the sort of 0, 1, 2 basis, it would look like zeros everywhere except for a 1 in the middle. Okay, so then we can work out P odd acting on the state psi would just end up being ket 1 acting on the inner product of bra 1 with psi, right? Then outer product. It's a great thing about bra ket notation. This just means an outer product of the vector with its dual, column vector with a row vector, which is a matrix, this matrix. But we can evaluate it just by writing it next to the psi and then contracting that bra with a ket into a bra ket. And so this ends up just being C1 times ket 1. Okay. Then psi P odd psi is just equal to C1 times psi with 1, which is now modulus C1 squared, as we found before. Okay, so if we had been doing a complete measurement, like we had before, where we sort of have one measurement outcome associated to each state in the basis, then our operators PM would all just be equal to the outer product of M with itself, and then this postulate would be exactly the same as the postulate we had before. Worth spending a minute to check that in your own time if it's not obvious to you. Okay, and then the new state would just be P odd acting on psi divided by square root of psi P odd psi. And this is indeed just the state 1, no matter what the initial state psi was. Okay. The operator P even is going to be equal to the identity minus P odd. So that's the matrix where we have a 1 in the top left and bottom right corners. And this can be written as the outer product of 0 with itself plus the outer product 2 with itself. All right, so it's the sum of the two projectors that you would have naively associated with 0 and 2 if you did a complete measure. Okay. And now, if we apply this matrix to the state psi, we do indeed get C0 times ket 0 plus C2 ket 2. It sort of kills the 1 component and leaves the 0 and 2 components alive. That's why it's called a projector. It sort of projects out those 2 components and gets rid of the rest. So our probability of getting measurement outcome that says it's even is equal to this, which is indeed C0 squared plus C2 squared. And finally, our new state, as we sort of guessed before, is a normalization factor times C0 times 0 plus C2 times C. Right, so it's just a part of the state that was even. Right, the new state is the part of the old state that was already even. Great.
Professor?
Yep.
Yeah, I have a question. So
Yep.
I'm trying to see why the even odd measurement operator is a complete operator. So
Oh, sorry,
I was
it's not a complete operator. It's not a complete measurement. By a complete measurement, we mean a measurement where the number of outcomes is equal to the dimension of the Hilbert space. Maybe
Yes.
you were meaning something different. Yeah.
No, I mean exactly the same. So I thought that it was complete, but I was thinking that that measurement operator only has 2 eigen subspaces, I think.
Yep. Yeah. So the odd even measurement is not a complete measurement.
Okay.
So if the measurement had been if we'd done a complete measurement, then the projectors associated to it would just be they would all just be an outer product of a bra with a cat, right? But in this case, we have P even is just the sum of two rank 1 projector. It's a rank 2 projector. It has a 2-dimensional eigenspace with eigenvalue 1, right? So that means it's not a complete measurement.
In that case, wouldn't you need the operator to be complete for the sum of all the projector operator to add up to the identity?
No. So we in fact define P even as the identity minus P odd. Just look at the two like matrix representations, P odd and P even, they add up to the identity, right? If each of the projectors was rank 1, i.e. it was just the outer product of a vector with itself, then you would need to have sort of 3 different projectors to add up to the identity, right? But because this P even has a 2-dimensional eigenspace, it's rank 2, then we can add up P even and P odd to get the identity. Is that clear?
Yes, thanks.
Great. Okay. So yeah, the definition I just gave for postulate 2 is sort of the really the most general one and like the right one. But it's not the most conventional one people use in quantum mechanics. So let's just see what that one is now. And the one people normally use, the sort of disadvantage of it, and the reason why it's not seen as the sort of most sophisticated one, is that it only makes sense if your measurement outcomes are numbers, right? So suppose the measurement outcomes M are all real numbers. Then what we can do is we can package all these projectors, PM, into a single operator. Which I'll call O, where O is just a sum over the values of M times M times P of M. Okay, so for any 2 sets of operators, PM, that differ in either one of the M's or one of the PM's, then I'll get different operators O, and I can recover the set of sort of M's and PM's just from the operator O, just by looking for the eigenspaces and eigenvalues. Right, the M's are the eigenvalues of this operator O, and the PM's are the projectors onto the eigenspaces. It's easy to check that the Hermitian conjugate of O, right? So the transpose complex conjugated of O is equal to itself. So O is what's called a Hermitian operator, Hermitian matrix. Moreover, any Hermitian operator has sort of orthonormal set of eigenvectors and eigenvalues, so it can be written in this form. So I can associate sort of M's and PM's to any Hermitian operator. So people will often say that measurements are defined by a Hermitian operator. It's often called the measurement operator. This is very convenient, and will do this all the time in practice. But I really want to emphasize that this is sort of not this is not always true. It's only true when the measurement outcomes M are all real numbers, okay? Of course, you can call your measurement outcomes whatever you want to some degree, so you can certainly always do that. But it's sort of restricting to say that your measurement outcomes have to be real numbers. In reality, they can be whatever the hell you want them to be.
Could you give an example when they're not real? Because it's sort of drilled into us.
So an example would be the measurement that was distinguishing whether M was even or odd, right? I could say that even is the measurement outcome 0 and odd is the measurement outcome 1, but it's I can also just call them even and odd. Another example would be the polarization of photon, right? Yes, on Thursday, measuring whether it was vertically polarized or horizontally polarized. Sure, I can attach numbers to those, but there's really no reason to do so.
Okay.
Okay, so one of the very nice things about defining measurements through this sort of measurement operator is the following. Let's say I don't care about all the possible outcomes and probabilities of my measurements. I just want to know the sort of expected value of M, right? I.e. sum over M times PM. This is obviously something that only makes sense if the M's are real numbers, but if they are, it's a pretty useful quantity. This I can clearly write as psi PM psi. Then by the magic of linear algebra, I can bring everything inside like this. So I have sum over M, P of M now inside the bra and the ket. So this is just equal to bra psi times the measurement operator O times ket psi. Okay, so this very simple formula, just like evaluating, column vector times matrix times row vector, will tell you the sort of average value of the measurement outcome. So this is a really useful thing. Another thing that is very useful, so commonly this notation we will just call expectation value of O, for very obvious reasons. Another thing that's very useful about just thinking about these measurement operators is that last lecture I claimed that you can't simultaneously do measurements in different bases. The sort of analog of this for partial measurements is that you can't simultaneously you can't simultaneously do two measurements unless they have a shared set of eigenvectors. Okay, that's really just the same thing. And in terms of measurement operators, then this can be written in a very simple way. It's the question of whether what's called the commutator of the two measurement operators, A and B, just means A times B minus B times A is equal to 0. Can't simultaneously measure them if this commutator is not equal to 0. Okay, people who are familiar with the uncertainty principle will be aware of how the commutator shows up there, but it's just a general thing that if two operators do commute, you can always have measured them one and then measure the other, and it won't change the outcome of the first thing because the eigenvectors are the same. But if they don't commute, then there will be at least some measurement outcomes for the first operator that are not possible allowed measurement outcomes for the second operator. And so doing the second operator will mess up the outcome of the first operator. Okay. Okay, so that's just a sort of couple of brief comments about how using this sort of measurement operator formalism lets you sort of do pretty simple calculations that contain a lot of information you want to know about what happens when you do the measurement. There's some particularly important examples that I just want to mention briefly that will show up all the time. These are the so-called Pauli matrices. You may have seen in discussion yesterday. So the first one is called the Pauli Z operator, sigma Z, or in quantum information, you commonly just write it as Z. That's the notation I'll use. And that is the matrix that in the 0, 1 basis, just looks like 1, 0, 0, minus 1, i.e. it's equal to outer product of 0 with itself minus the outer product of 1 with itself. Okay, so two measurement outcomes associated with that are the m equals 1, which corresponds to the state ket 0, and m equals minus 1 corresponds to the state 1. Right, that's just reading off the eigenvalues and eigenvectors associated with this operator. So what does that mean on the Bloch sphere? All right, so 0 is at the North Pole. 1 was at the South Pole. Turns out, you guys can check this. I'm not sure if it's going to be on homework, but it's certainly worth thinking about. If I have some state psi that's sitting in an arbitrary point on this Bloch sphere, then the expectation value of this measurement is actually equal to the height on the z-axis of the state. Z-axis of the state psi. So for example, the North Pole is state 0, and that has, it's at height 1 on the z-axis, and indeed we get measurement outcome of 1 with 100% probability. It's the state, the state 1 is at the South Pole, and that corresponds to measurement outcome -1. If I have some random state somewhere on the side, then when I do this measurement, I'll always get either 1 or -1. Those are the only two measurement outcomes, but the probabilities are such that my sort of expected value is given, the expected value of the measurement is given by the height on the z-axis. So if it's on the equator, it's 50-50, expected value of 0, 50-50 of 1 or -1. It's higher up than that, it's positive, lower down, negative. There's also two other operators that are sort of equally important, which are the Pauli X, which is like this. It can also be written as ++, minus, minus, minus. So remember, plus and minus were on the left and right, respectively. And this, we have the expectation value of x is equal to the position on the x-axis, unsurprisingly, given the name. And finally, we have sigma y, y is equal to minus I
Plus
pi. So what was that?
No, I was just like saying plus I.
Yeah. And this can be written as the plus I state minus the minus I state, which were respectively at the front and back, i.e. the extreme points on the y-axis, and unsurprisingly, the expectation value of y for some state tells you the position on the y-axis. So again, yeah, very natural interpretations in terms of the Bloch sphere. So let's very briefly comment on what these sort of operators mean in a sort of concrete example, which is going to be the spin of an electron. It's another thing that, just like the polarization of a photon, that is a natural qubit. There are two states to the spin of the electron. So the spin of the electron has a basis that consists of sort of spin up, which I'll treat as the zero state for purposes of comparing it to these matrices, and spin down, which means it's spinning downwards in some particular axis, which I'll interpret as the state 1. In this case, then this operator Z has +1 for if it's spin up, has -1 if it's spin down. So this operator, as said, is just measuring the angular momentum of the particle in the z direction. Similarly, for the x and y operators, they're measuring the angular momentum of the particle in the x and y directions. So for example, the plus state, which is 1 over square root of 2, the up state plus the down state, is a state where the particle is sort of definitely spinning to the right. It definitely has positive angular momentum in the x direction. In fact, for an electron spin, the points on the Bloch sphere, this is again related to something that will come up in your homework, are all associated to eigenstates of angular momentum in the corresponding direction. So for example, this state psi up here pointing sort of up and to the left, that is an eigenstate of the operator that measures angular momentum in that sort of diagonal direction. Okay. So we have about 20 minutes left. Going to talk about briefly about our first sort of application of a quantum information concept, quantum key distribution. Going to talk about a particular protocol, in fact, for doing that, which is called BB84. Why BB84? Because it was first introduced by Charlie Bennett, and Gilles Brassard, and they introduced it in 1984. Which may sound sort of kind of recent compared to a lot of developments in quantum mechanics, but this was really the very beginnings of people starting to think about quantum information. Very, very early stages, I'm not sure. So around the time Feynman was first suggesting the idea of a quantum computer, that sort of era. Okay. So the setup is the following. We have some person, Alice, which I'll draw in a very gender normative way. But there you go. And we have a person, Bob. And what they want to do is they want to end up with some secret numbers, some secret bits, zeros and ones, that only they know and no one else does. Because if you have that, then you can share any secrets you want by using things like one-time pads and stuff, right? You can have perfectly protected security that no one can ever hack. You just apply like a random, just the simplest way is if you have 100 bits that nobody knows, but you and the person you're sending it to know, and you want to send a 100-bit long message, then you just bitwise add your message and the secret bits. And then from the point of view of someone who doesn't know the secret bits, then the message you're sending has no correlation with the actual secret message you're encoding. Okay, you can have perfect cryptographic security. The trouble is, of course, getting these shared secret bits without someone else learning about them, right? So if you're in the same place, if you're in a top secret room, you could just tell them to each other and remember them. but often you might not be able to do that, right? You're trying to communicate with someone's a long way away and you've run out of secret bits. You need to send more to them. So what we're going to assume is that Alice and Bob can talk to each other classically. They also have the ability for Alice to send qubits to Bob. But there's some evil person, Eve, maybe not evil, whatever. Eve is hanging around and she is spying on what's going on. She can intercept their messages and look at them, maybe measure them and stuff. So Eve is spying. They don't want Eve to find out the secrets they're saying. She works for the other side in a war or something. So we want these secret bits to be known by Alice and Bob, but not Eve. Okay, how do they do this? Alice randomly chooses A, some sort of zeros or ones, and B chooses a basis. So either 0, 1 basis or the plus minus basis. Okay, and then she sends qubits to Bob, where the state depends on her bit. So if she chose 0 for a bit, then she sends either 0 or plus, depending on which basis she chose. And for 1, she sends either 1 or minus. Okay, is that clear to people?
Yes.
Awesome. So now Bob is going to measure. Bob at the moment does not know what basis he's getting these qubits are encoded in, but he just receives them. Maybe it's hard for Bob to store them. Maybe the send is like photons or something. So he's just going to measure in a random basis again. Either the 0, 1 basis or the plus minus basis.
For when Alice sends qubits to Bob, shouldn't the 1 be state 1 and
yeah,
minus
sorry.
minus?
Yep, that was a typo. Yeah. So if Alice is wanting to chose 1 as her classical bit, then she should, and she's using the 0, 1 basis, she should send a 1 rather than a minus. Sorry. Apologies for that. Okay, so Bob is just going to measure when he gets it in a random basis. And now that they've done all this measurement, not before, Alice, Bob will use the classical information to sort of compare notes, right? And say, oh, that one I measured in, I prepared in 0, 1. Oh, I measured it in plus minus, and so on, okay? On their choice of bases. They don't say anything about their measurement outcomes, okay? If they chose different bases, they'll just throw away the qubits. Okay, we're imagining we're doing this on a large number of qubits. It doesn't really matter. You lose 50% of them, whatever. It happens. Okay. On the remaining qubits, Alice and Bob are going to take some. So if they hadn't got spied on, then all the remaining qubits then Bob's measurement should equal Alice's bit. So they should have successfully shared some secrets, right? These are going to end up being the secrets, but they didn't want to just take it on trust that everything works out. What they're going to do is they're going to take some of those qubits and just check them. Again, they'll just do that using their ability to like send classical messages to one another. Okay. If they all agree, they'll go, okay, looks good. Use the remaining still secret ones as the secret key. Okay, so everyone's clear on what that protocol is, like what the different steps are in it?
So when you say Bob's measurement is equal to Alice's bit, that's if Eve is not measuring so far.
Yes, right? so if Eve does nothing. If the protocol is succeeding, then that will happen. Okay, so let's say Eve is trying to do some good spying and work out what this secret key is. What can she do? Option one would be to spy on the classical communication, right? But this doesn't really tell her anything. Even if she's able to hear all the classical communication, she can't get any useful information out of it, because all they're doing is like comparing the bases they used after it's already been sent, and comparing notes on some qubit, some of the secrets that aren't the ones they end up using. Okay. Option two is she could try to measure the qubits while they're being sent, right? These are the things that are eventually going to get the usual information. Of course, when she does that, she doesn't know what basis Alice used to encode the state, right? Because even Bob doesn't know it at that point. So, you know, an obvious strategy that she might try, you could get more sophisticated, and we're not really going to talk about trying to rigorously prove that she can't ever learn the secret, but an obvious strategy might be that she guesses a random basis. I'm not going to go through the details of this because there's very related stuff on your homework, but the basic point is 50% of the time she guesses the wrong basis. And then because measurements in quantum mechanics inevitably change the state, then once she's done that 50% of the time, Bob and Alice will end up disagreeing on their measurement outcomes. Well, Bob's measurement outcome will disagree with Alice's encoded bit. So as long as Alice and Bob tests sort of sufficiently large random sample of the qubits, then they're going to spot her spying. So again, will fail because Alice and Bob will just give up and try some other method of sharing secret keys. Okay, she hasn't managed to learn the stuff without them knowing that she learned.
I just have a question.
Yep.
It's just like something about the protocol. When you say that Alice and Bob compare their measurements classically, do you mean like they just like talk over the phone whether they got
exactly.
Okay.
Yep. They literally phone each other up because of that stuff. They don't care who like is able to hear it. They just need to talk to each other. So they can literally make a unsecured phone call and just say, in practice, you'd have to do it with like a computer or whatever. And so they wouldn't be literally talking over the phone, but they would do something. But this gets into the third approach, which is what Eve can do and can potentially succeed and need to worry about. And that is something that in cryptography is called a man-in-the-middle attack. So here's what Eve does now, is she intercepts the classical communication and replaces it, doesn't just spy on it, she actually replaces it with like fake communication. So what she would then be able to do is Eve can pretend to be Bob, to Alice, and tends to be Alice to Bob. Right? She's able to do this, then, you know, no matter what she's doing with the qubits, she can replace the qubits with her qubits and so on, have them be completely different to the initial ones. And yeah, and there's no way that they can spot that unless they have some way to like verify that they're really talking to the real person, right? So this succeeds unless Alice and Bob have some other verification method. For example, they could like recognize each other's voices on the phone. And if unless Eve has some very fancy high-tech voice simulation stuff, then there's nothing they can do about that. So there is a great question in the chat, which is, couldn't Eve just copy the qubit as it is being sent? The answer is no. As someone has also rightly pointed out in the chat, it is not ever possible to copy qubits. And this is because of something called the no cloning theorem. So I'm going to try to put that, it's not on this week's problem set, but I think I will put it on next week's problem set. Or we might cover it in the lecture. It's just a theorem that you can really quite easy to prove, though it got someone a Nature article in the 80s or something, that there is just no unitary map that for any state psi takes it to 2 copies of psi. So yeah, it turns out, you know, you should not take this list of checks as like conclusive. There's an awful lot of other things that you could imagine doing. But it turns out that this protocol is genuinely secure if done right, which is, you know, it's really cool, right? It's something that you just can't do classically. There's no way to, there's ways you can do stuff that, there's cryptography that is protected by sort of the computational difficulty of hacking it. But there's no way to sort of share a secret key like that in a way that is just like protected by the very back to the laws of physics. You know, that there's just physically no way that anyone, even with an infinitely powerful computer, could hack what you're saying. So yeah, that is all for today. The homework is due Friday at 6 p.m. My office hours are Thursday, 4 till 5 p.m. I can't remember when Nam's office hours are off the top of my head, but I think he has ones today and maybe ones yesterday as well. Is that right? It's on the piazza. Yeah, next lecture on Thursday. We'll cover more about postulate 3, in particular how it leads to this famous equation of quantum mechanics called the Schrödinger equation. And then we're going to talk about how to understand the states of multiple qubits, and we'll come across entanglement for the first time, which is always cool. So yeah, see you all then. If you want to stick around now to ask me more questions, I think I will stop the recording now, but feel free to do so.